How tiny tugboats move massive cruise ships is a massive mechanical cheat code. It's a high-stakes exploitation via levers, and even a controlled collision that defies common sense. The second a luxury liner enters a restricted channel, it loses all its ability to steer. This is the velocity failure. Marine steering relies on high-pressure water displacement. Once the hull drops below 4 knots, the massive rudders at the stern stop biting the water and become useless metal fins. You are now responsible for a mountain of steel. Without a constant stream of water pushing against the blades, the captain is effectively holding a disconnected steering wheel that drifts toward a concrete seawall. There is zero friction to stop this slide, and the main engines are far too sluggish to react to a sudden gust of wind. It's a terrifying reality, where the ship is just a massive, unguided projectile. But just as the hull threatens to drift off course, a 3,000 horsepower floating anchor latches onto the side to execute a high-stakes braking maneuver. Most people assume tugboats are there to shove a ship forward, but their most critical job is actually acting as a massive, floating brake pad. Even at a measly 2 knots, a cruise ship carries more kinetic energy than a skyscraper in a windstorm. If that hull touches the concrete pier at even a fraction above the planned speed, the steel crumples. This is why the tug on the dockside isn't pushing the ship in, it's actually pushing outward against the hull to resist its momentum. It's like a wrestling match where the tugboat uses its engines to fight the ship's drift, turning a catastrophic impact into a gentle lean. By squeezing itself between the vessel and the berth, the tug acts like a hydraulic shock absorber, bleeding off the ship's energy before it can snap a mooring line or crush a fender. This parking job is a 3,000 horsepower intervention designed to stop a slow-motion disaster. To understand why this intervention is so difficult, you have to look at the sheer physics of the size gap between the two boats. To put the scale into perspective, a modern harbor tug is usually about 30 meters long, while a Triple-E-class container ship or a massive cruise liner displaces roughly 220,000 metric tons. That creates a size ratio of approximately 1 to 660. To visualize that on land, it's the equivalent of a single Labrador retriever trying to steer a Boeing 747 down a narrow hallway. The only reason the tug doesn't get flattened instantly is that the physics doesn't care about size, it only cares about where you apply the force. Because the tug can generate nearly 100 tons of bollard pull, it can manipulate the ship's center of gravity like a lever. It's an engineering heist where a tiny machine dictates the path of a giant simply by knowing exactly where the handle of the ship is located. However, applying that force at the wrong angle would be useless, which is why the lever logic of the ship's hull is the captain's secret weapon. Think about a heavy door. If you try and push it from the hinge, it won't budge, but a tiny push of the handle swings it wide. This is the torque hack that tugboats use to dominate ships 600 times their size. By positioning themselves at the absolute tip of the bow or the far edge of the stern, they maximize their distance from the ship's center pivot point. This converts a relatively small push into a massive rotational force that can spin a 200,000-ton hull like a needle on a compass. It's all about exploiting the physics of a lever to make the ship work against its own weight. By targeting the handle of the ship, the tugboat gains a mechanical advantage that makes the giant vessel feel weightless in the water. But even the best lever is useless if you can't change a direction instantly, leading to a propulsion system that feels like it's breaking the laws of physics. Old-school tugboats had to back and fill like a clunky truck, but modern versions use something called a Z-drive. Instead of a fixed propeller and a rudder, these machines have 2 massive pods under the hull that can rotate 360 degrees independently. This allows the tug to generate full power in any direction, sideways, diagonally, or spinning on a dime. The result is a vessel that can push a cruise ship toward the dock, while its own hull is pointing a completely different direction to fight the current. This vectoring of force means the tug doesn't waste time maneuvering. It just points the thrust where it's needed, and the ship reacts instantly. It is pure directional violence packaged in a hull that can survive the crushing pressure of a slow-moving mountain of steel. However, all that agility is useless without the raw grip needed to move that mountain, which brings us to the industry's most brutal metric: bollard pull. In the tugboat world, horsepower is just a vanity metric. The only number that matters is bollard pull. To measure this, engineers literally tie the tug to a massive steel post on the dock with a heavy-duty cable and tell the captain to floor it. The tension on that line, measured in metric tons, is the bollard pull. A standard modern harbor tug can generate about 80 to 100 tons of this raw stationary force, enough to snap a skyscraper's foundation if it had a place to grip. It is the maritime equivalent of a world-class powerlifter, holding a heavy weight perfectly still against a shifting floor. Without this verified pulling power, the tugboat would just be spinning on its wheels in the water while the ship drifted away. But even with 100 tons of pull, a sudden change in the weather can turn the entire ship into a giant uncontrollable sail that no amount of engine power can stop. The most dangerous enemy in a harbor isn't the water, it's the air. A massive cruise ship or a loaded container vessel presents a windage area that can be over 40 meters high and 300 meters long. To a stiff breeze, that hull is no longer a ship, it's a giant unyielding sail. If a 20-knot gust hits that surface area, it generates hundreds of tons of lateral force, pushing the vessel sideways with more power than its own bow thrusters can handle. Now the tugboat transitions from a helper to a survival tether, using every ounce of its bollard pull just to keep the ship from being blown onto the rocks. The pilot on the bridge has to calculate the leeway, the sideways drift caused by the wind, and coordinate the tugs to counteract a force that is invisible but incredibly violent. It's a constant high-tension balancing act, where the tugs must pull against the wind's shove to keep the ship centered in a channel that might only be a few meters wider than the hull itself. But even after winning the battle against the wind, the most expensive 10 feet of the entire journey are still waiting at the edge of the concrete. The last 10 feet of a 10,000-mile voyage are the most expensive. At this range, there is no room for good enough. If a 200,000-ton vessel approaches the dock just 1 centimeter per second too fast, it creates a fender crush that can split a hull or buckle a multi-million-dollar pier. The tugs are now in a state of surgical resistance, providing microbe adjustments to the ship's momentum. One wrong radio command or a single mechanical lag in a Z-drive could turn a routine docking into an economic disaster. You're looking at a $300 million asset being held in place by a machine that looks like a toy, proving that in the ocean, precision always beats scale. The next time you see a tiny boat nudging a floating city, remember that you aren't looking at a helper, you're looking at the only thing keeping the harbor from becoming a scrapyard. Investing in the right force at the right time is the difference between a successful delivery and a catastrophic insurance claim.